Hi everyone. My name is Harini. I'm a PhD student at Interdisciplinary Center for Water Research in Indian Institute of Science, Bangalore. Currently, I'm taking NPTEL. I'm doing NPTEL TA for the course Watershed Hydrology offered by Professor Rajendra Prasad sir from IIT Kharagpur. So today's topic will be about floods. What are the causes of floods and how we can design hydraulic structures for floods, and we will be discussing various methods related to that. Okay, and we will be talking about the terms like risk reliability also. So if you have any questions related to these topics, you can ask me. Currently, I'll give a summary of the topic, and I'll solve few problems related to this. If you have any questions, you can raise the hand or unmute and speak up. Okay. So first, what is floods? So as we know that whenever the water overflows from any river or any channel and it inundates the area around it, that is called as floods. Okay. So floods. The formal definition will be high water stage in which water overflows its natural or artificial banks onto normal dry land such as rivers inundating its floodplain. Okay, what are the causes of these floods? So these floods occur generally due to heavy rainfall or rapid snow melt, storm surge, dramatic tropical cyclone, or tsunami in coastal areas. Like for example, heavy rainfall, rapid snow melt, and tsunami in coastal areas, cyclones, etc. causes floods. Okay. So there are different types of floods based on where the flooding is occurring and what is causing those kinds of floods. Okay. So first we will be talking about river rain flood. So in this case, river rain means like the rivers, right? So the overflow of water within the rivers and inundating the area around it is called as river rain floods. Overflow of rivers due to excessive rainfall, rapid snow melt, or a combination of factors. So combination of factors means suppose if there is the reservoir is full and we know we are expecting that there might be flow coming into the reservoir. So what we will do is like we will lift the barricades of the reservoir which causes floods. So this is also a factor, and along with the water that is coming out of reservoir to the downstream, and also if there is rainfall occurring which is causing overflow of rivers. It's like a combination of different factors. So, river and floods is nothing but the overflow of river. It can be due to excess rainfall, snow melt, or any combination of these kind of factors. Okay, so in India, mostly we will be seeing out of river and floods. Okay, and this can be due to the sediment loads or inadequate carrying capacity of the channels, because From upstream, whenever there is a flow coming up, the sediments get deposited in the downstream areas and the channel size. Suppose we have a channel like this, because the sediments gets deposited, you can see there is a this part of the channel is filled by sediments. Then the volume through which the capacity of the channel reduces to hold the water, right? So, because of the sediment deposit, and this causes inadequate carrying capacity of the channel, which is leading to flooding in some areas of India as well as any other countries also. And mostly in case of river and floods, river banks and floodplains, floodplains are affected. Okay. So next type of floods is coastal flooding. So as we know, like in case of coastal floods like in Orissa or Chennai, Mumbai, we know that because of storm surge or like water level rise in the oceans or heavy rainfall, both combined or individually also can cause floods in these kind of areas. So mostly storm surge, high tides, hurricanes, or tropical cyclones cause floods in coastal areas, which inundate coastal areas by salt water. Because all these are due to rise of water level of the oceans, which is the salt water, right? So this salt water will inundate the areas in the coastal plains, and mostly you see this in Andaman and Nicobar Islands are highly susceptible for coastal flooding. Also, in case of Lakshadweep Islands, high coastal flood hazard. These two come under high coastal flood category. Okay, Andaman and Nicobar, Lakshadweep. These two come under high coastal flood category. Okay. So the next type of flood is flash flood. So as the name is itself suggests, it's like the event will occur very quick. Okay. So rapid rise and fall in the water levels involving high discharge causes flash floods. Okay. So since they occur very quick, the damage also will be very high. They lead to very high damage because we don't have any time to take precautionary measures or do mitigation or evacuate the people, etc. Right? So this causes high damage. Also, it mainly occurs when the flow can be very quick, which can happen in hilly areas, right? Because of the slope, the flow is very high, and it will be very quick, and so this is mainly seen in hilly areas. So this kind of flash flood can be due to very high intensity of rainfall in very short duration period, or like thunderstorms or cloud bursts, depression, cyclones, and the sudden water release from dams, reservoir, etc. All these can be factors which can cause flash floods in any area. It can be in urban, it can be in rivers, or it can be a coastal flood also. Okay. The next one is urban floods. So, since most of these areas which used to be forest or agricultural lands previously, are mostly converted are getting converted into urban areas. Okay, so that's why we and when they are converting into urban areas, there were not proper regulations or control that has been applied in the encouragement of floodplains. So suppose the lakes, where there will be some boundary beside the lakes, which should not be used for any construction purpose, so that whatever water coming into the urban areas can get stored in this lake. So but there are constructions going on, so all these are resulting in urban floods, and also the stormwater drainages that are designed for the urban areas are not sufficient because of the climate change. The intensity of rainfall is also increasing, and which is leading to the inadequate capacity of the sorry, the inadequate capacity of the drainages are leading to floods in urban areas. Also, there can be some clogs that can occur in the drainages, which is also causing urban floods. So then there are many reasons what are resulting in urban floods. Okay, so the lack of regulation and control in urban areas, there has been significant encroachment in floodplains. So floodplains are like, suppose as I've discussed, there is a river, and on both sides of the river, we consider it as floodplain, because if there is some overflow from the river, oh, this part of the area will get flooded for sure. Okay, so those kind of areas are called as floodplains. Suppose in lakes also that's the case, right? So encroachment of these floodplains, also inadequate capacity of stormwater drainage system. These are the main reasons that are leading to floods in urban areas. And the last type of flood is glacial lake outburst floods. Oh, yes. So, as the name suggested, we can see there is a glacial involved. So, because of glacial melt or something, the flood can happen, which is very rapid. Okay, kind of like flash flood, but the water stored behind a glacier or a moraine is released suddenly. So, like melting of ice blocks or glaciers, which are very quick actions. Sometimes it can be quick also. So, in that case, there can be flash floods that occurs. So, we have seen in Uttar Pradesh also, like there were flash floods events that occur due to the melt of avalanche or like glacier in these areas. So, now let's look into what are the causes of floods. As we have discussed previously, also the main causes of floods are like heavy rainfall events. First one is, so if there is a heavy, intense, and prolonged rainfall, especially during monsoon season, the soil also will be saturated, and which is leading to whatever the rainfall that is falling, it will be coming out as runoff mostly. So, which causes high runoff values and causes floods in the areas. So, intense and prolonged rainfall, especially during monsoon season. Next types of flood Next types are storm surge. So the tropical storms, hurricanes, and cyclones, particularly in coastal areas, causes these storm surges, like rise in the water level of ocean and cause floods. Okay, tropical storms, hurricanes, or cyclones, particularly in coastal areas. Next is snow melt. So rapid melting of snow also cause floods, as we have discussed. We have discussed in glacial lake outburst floods also, right? Next is river overflow. So as we discussed, like when the river water in the river overflows to the banks, then it causes floods. Next, urbanization. Why urbanization causes flood? So when there is when we have already discussed earlier that when the land is well, when in the land cover is forest or any agricultural land, the infiltration capacity of the soil will be more because water can be held by the roots of the plants. But when you convert this kind of land into urban land, like concrete structure you are constructing or a pavement you are constructing on the land, what will happen? Whatever the rainfall that is falling is mostly going into runoff without getting infiltrated. But there can be very initial abstractions due to interception also. But the amount that can be stored in these kind of losses is very less compared to infiltration. So that is causing more runoff in case of urbanization. So in case of urbanization, the urban development leads to increase in risk of flooding because the infiltration capacity is low. Whatever the rainfall is falling, it is going as runoff. So that is because of reduced natural permeability of the soil, of the surface. Next is deforestation. So as I have discussed earlier, we know that the forest can reduce 20 to 30%, 40% of rainfall by capturing its infiltration. So only the 20 to 40% of runoff is reduced if we have a forested area. But without this forested area, that means deforestation is happening, it is leading to 20 to 40% increase in the runoff. Right. So if there is increase in runoff, that means there is a flood event which can occur easily, prone to flooding. So deforestation reduces the ability of natural landscape to absorb and retain water. Okay. So, as we have discussed, 20 to 40% of increase in runoff can be observed when deforestation is there. But when there is when the area is covered with forest, you can see comparatively it can store 20 to 40% of runoff. So the next topic is what are the consequences of floods? So as we have this, we know that we have seen lot of flood events that occur in our almost every year in different parts of the world, and you can see there are a lot of losses in the lives of the people and loss of life, and due to flooding, the properties, we can see property damage. The water gets entered into houses, which damages the furniture and all the materials inside. Also, like you can see the cars floating in the floods. Right. So the cars also get damaged. So there can be lot of property damage that occur due to flood, and it also causes erosion of soil erosion, and collapse of the buildings, etc. Then there are a lot of economic losses also, because whatever infrastructure that structure that got damaged due to floods has to be repaired, and we have to support the people who has suffered from the flood. So we have to government has to provide financial support to those people as well. And there will be psychological and social aspects. When if we know that the suppose area is a village or any area is getting flooded, people get migrated from that area. So there will be a displacement of people, and this flood water, whatever is coming, it won't be pure. It will have any all kind of dirt particles, chemicals that are on the roads or on the surfaces, right? So which causes contamination of water sources, because at the end all this flood water goes into any lakes or rivers or any water source itself. So all this dirty water, that is flood water, is causing contamination of the water source as well. And then this contamination will increase the risk of diseases. And also, you can see it will impact agriculture, because if the plants don't need that much of water, because of lead, the water get stagnant in those fields, and it will cause damage to the crop. And there can be soil erosion due to the floods, so which is also impacting the agriculture. And there will be disruption of services. So when there are floods, no one can go out of their houses, right? So there cannot be any service that can be provided, and also there won't be any electricity will be there. So there won't be any services which can be provided to the people during these kind of events like floods. And there will be lot of environment impact, and also it impacts the biodiversity. Okay. So in India, there almost 40 million hectares of land is susceptible to floods. Okay. And sir has given an idea of which parts of India can get easily flooded, and why and the reasons for it, etc. So basically now we will talk about like Indian river systems, which are like there are majorly five classes in this. First one is Brahmaputra region, which involves Brahmaputra plus Barak rivers. Okay. In this region, mainly heavy rainfall, seismic activity, and vulnerable hills causes frequent and severe floods. Okay. Heavy rainfall, seismic activity, and vulnerable hills are leading to frequent and severe floods. Next is Ganga River region, In this, mostly overflow and alterations in the course of the northern tributaries of Ganga River are mainly leading to floods. Okay, so overflow and alterations in the courses of northern tributaries of Ganga River is leading to flooding. Okay, and the third category is northwest river region, which faces very limited flood issues. Mainly, the problem is the drainage congestion that occurs in these kind of rivers. Drainage congestion is primary concern. Okay, then the fourth and last one is Central India and Deccan region. So, mostly east coast of rivers embankment. So there will be reduced flood problems in these kind of areas. So east coast rivers are embankment. So reduced flood problems. Embankment means we put if you remember there we put some soil or any structure on the banks of the river so that water can raise till to that height. Okay, so if it can suppose this is the channel or the cross section of the river, what we will do is we'll put some soil structure or some soil or any concrete structure along the course of the river. Okay, so that the water can raise even if it raised till here also there won't be any problem. So these are called as embankments. So this will reduce the flood problems. And it also has stable courses with adequate natural bank capacity, except in delta areas. Okay, so now let's look into flood severity assessment. That means how we will know like how much severe flood can occur or like it has occurred. Okay, so by examining the rainfall and precipitation values, we know that whether the flood event will be severe or not. So if there is heavy rainfall event that is occurring, then which causes high flooding. So if there is low rainfall, then it might not even cause any flood. Okay, by analyzing this rainfall data, we can understand the severity of the flood and also the data like river stage or stage means river height. Okay, the water depth is called as stage. Okay, or the discharge gauging. So from the gauges, we can get the stage that is water depth or the discharge values, which we can from that also we can understand the flood severity. If there is high stage or high stage means suppose this is the cross section. If the water is here, obviously the depth will be higher. If it is here, the depth is more, right? Or if the discharge is high, that means a lot of volume of water is going to the downstream part, so which can lead to flooding. So based on the data like stage, discharge, we can understand the severity of the flood. Next, floodplain mapping. Floodplain mapping means like we can identify the areas which are prone to flooding, or the suppose this is the river cross section. This will be the floodplain, right? This will be mapped beforehand. So for if there are rivers which are getting frequently flooded with a very high intensity, okay, because of high intensity rainfall or anything, high severe floods, this flood plain, that means the this lot of area will get flooded by the very high severe flood. Okay, so if the severity of the flood is low, then only it can flood very small portion of the floodplains. Okay, so by that also we can get an idea. So suppose in case of Ganga river, like we can see a very high floodplain because it can the severity of the flood is very high compared to other parts of the India. So weather forecasting. So by getting an idea of how much rainfall we can receive in future, that is means we are forecasting. So from that we can know how much of runoff or discharge can occur in rivers or any area, and based on that we know how severe it can be, right? Then these hydrological models, using the weather forecasted data, we will generate surface runoff or overland flow so that we can visualize in 2D or 1D format which areas are getting affected and what can be the depth of the flood, etc. Okay. Next is flood hazard maps. So in this, we will identify the areas which are more prone to flooding uh, in relatively. Suppose in Bangalore itself, we are considering then entire Bangalore cannot get flooded at the same severity. There can be few areas which are flooded more frequently and more severely compared to other areas. So we will identify these kind of hotspots, and then we will try to employ some mitigation methods for to prevent flood in these kind of areas. Then using remote sensing data. So from the images from the satellites, we can identify the areas which are actually getting flooded when there is a rainfall event occurring. So NRSC does these kind of activities as well, and providing early warnings system. So if we have weather forecasted data and we know this much amount of runoff or discharge is going to get received, then we can provide early warning to people or to the government, which will take actions in mitigating these kind of floods. And community reporting. Okay. So if you look here, based on the severity of the flood, we have different colors. Suppose if the color is yellow, then there is action to be taken. The flood severity is given action code. And if the color is purple, then there is a major flood event that is occurring. And there is also a definition what it is. Like suppose if it is a yellow color, an established gauge height which when reached to a rising stream, lake or reservoir represents the level where action is taken in preparation for possible significant hydrological activity. Okay, but in case of major flooding, the you see the definition: extensive inundation of structures and roads, significant evacuation of people, and or transfer of property to higher elevation. So you can see the difference. In this case, in yellow case, we are saying that the maximum height, suppose this is the depth of the channel, the water is still here. And in case of reservoir, there will be a level till which only there will be a storage capacity of the river, of the reservoir, which is reached. And we have to take some action to prevent in any hydrological activity. That is, if there is any more water coming up, then we cannot handle it. So that means that's a low. But in case of major flooding event, there is already flood that has occurred. and people are getting migrated from that place to another place. Also, property is getting submerged, etc. So you can see the severity is increasing from up and up to down, and the colors are given yellow, orange, red, and purple. So you can see read these definitions as well to understand what are the different flood severities like action, minor flooding, moderate flooding, and major flooding. Okay. So now let's talk about design flood. So now that we have talked a lot about how floods are occurred and what are the causes of floods, what are how floods can affect people or the property or any country, okay, and what are the different types of flood. So how? So then what should we do? So we have to design the structures, hydrological structures, hydraulic structures, like drainage structures or dams, reservoirs, anything to hold this kind of water, right? So how we will know how much amount of water it should hold? So for that we will have some uh, one term called design flood. So it is the process of in this process of determining the appropriate standards and criteria for designing structures to withstand or manage flood events. Okay. So we will have a condition like suppose there is a drainage in urban areas. It should hold this much amount of water in it. So that we will get from uh design flood. Okay. And in case of reservoir, it should hold huge amount of water compared to any drainage, right? So all these values will fix using design flood theory. Okay. So it's used for selected. It's selected after considering both economic and hydrological factors. And mostly it is related to project type. As I told, suppose if it is a dam or reservoir, it should hold huge amount of water. So if it is a drainage, it should hold water at that instant and there will be always flow occurring, right? So the capacity of the drainage will be less. So design flood will depend on the type of the project. Okay, then how now we will see how to select flood magnitude for hydraulic structure design. Okay, so mainly there are three terms which you have to remember: standard, project flood, SPF, in which we will estimate the flood magnitude flood that likely to occur from the combination of meteorological and hydrological conditions which are reasonably characteristic of drainage basin being considered, but excluding extremely rare combination. So that is rare, extremely rare combination of meteorological and hydrological condition. And this is called a standard project flood. Okay, but there is one more probable maximum flood. It also has similar, it's called as PMF. It also has similar definition, like we will estimate the flood that likely to occur from the combination of different meteorological and hydrological conditions. But here it includes extremely rare and catastrophic floods, and they are usually confined to spillway design of very high dams. Okay, is this clear? In case of SPF, we will look into different combination of meteorological and hydrological condition, and the maximum flood that can occur is considered as standard project flood. But in case of probable maximum flood, we will take all these extremely rare cases or catastrophic flood events also, and using that we will define the probable maximum flood that can occur. So next third one is design flood. Okay, so now we have discussed already SPF and PMF. So design flood is the flood magnitude that we are using for the design purpose. Okay, so flood value, flood adapted for design of hydraulic structure. So it can be either SPF or PMF that we are adopting for designing the hydraulic structure. Okay, so whatever, if we are adopting the SPF, then the design flood is SPF. If we are adopting PMF, then the design flood is PMF. So different guidelines for this design flood has been given by CWC India and also ISI. So in case of ISI, they are saying that the flood magnitude will be a function of size, hydraulic head, and gross storage of the structure. So you can look more information about this in Sir's lecture. So now let's discuss about different methods of flood design. The first one is physical indication of past floods. Okay. So this how we will know there can be flood marks. Okay, suppose there is a flood event that occurred. The dirt or all the marks, the soil aeration, etc., which will leave marks on the surface. Okay, using those marks or by inquiring the local people, we will know till what depth the water can rise in in flood events in any basin, or also like we can know how much amount of floodplain can get flooded. All these kind of data we can get from flood marks or local inquiry. So, and using that, we will calculate maximum flood discharge. How we will calculate using just these ideas? We can use this Nix equation or Chassis equations, right? Because from that, from these marks, we can get the idea of the area, cross-section value, and also slope we can find. So then we can easily apply Manning's equation and also Chassis equation. Okay. So the next method is envelope curves. in which like we will have a curves of saying like suppose this is the size of the we have size of the catchment, and this can be the for this written period this much of flood event discharge can occur. Okay, so this kind of information can be prepared for the catchments, and the catchments that have comparable climate and topographical characters. So we can use if a catchment 1 and catchment 2 has similar climate and topographical conditions, then the envelope curves that we have designed for catchment 1 can be used for catchment 2 as well. So all these things we can apply. Next method is using empirical formula, which we have already discussed. Like we have different empirical formulas to calculate the peak discharge. Suppose here, if you see the for Dickens, in Dickens formula can be used only for central and northern parts of the country, and here it is defined as QP equal to CD into A power 3 by 4. And in Rives formula used for Tamil Nadu region, and QP is equal to CR into A power 2 by 3. And English formula is used for mostly western Ghats of Maharashtra, where QP is equal to 124A by root of A plus 10.4. In these all these cases, QP is the peak discharge and CD is the quotient of Dickens formula. CR is for Rives formula, the quotient, and A is the area of catchment in kilometer square, and you will get the peak discharge in meter cube per second. So whenever you are trying to substitute area, remember that it has to be in kilometer square. Okay, otherwise the, whatever value that you are getting won't be in meter cube per second units. So Dickens constant will vary from 6 to 30, and Rives quotient also will vary from 6 to 11, I think. Not sure. So the next method is rational method. This also we have discussed. We will calculate the peak discharge using formula C into I into A, where C is the runoff quotient, I is the intensity of rainfall in meter per second, A is the catchment area in meter square. So then you will get QP in terms of meter cube per second. Okay. So if you remember, the intensity of the rainfall should be falling uniformly across the catchment, the assumptions in this method. And also it should occur for a duration equal to or greater than the time of concentration of the basin. And how the time of concentration can be calculated? It is TC equal to 0.01947 into length power 0.77 into slope of the basin power minus 0.385. This S is the slope, this is the length of the stream. Okay, so these two methods I went little fast because we have discussed earlier. But if you have any doubts, you can raise and ask me questions related to this. And the next method is unit hydrograph. So if you remember, unit hydrograph is the hydrograph for a 1 centimeter excess rainfall. Okay. So from this, what we can do, the peak flood value can be obtained, right? So suppose we have for unit excess rainfall, we know the hydrograph. Suppose we know the what can be the rainfall event that can occur, right? So using that we can generate a flood hydrograph, and from that flood hydrograph we know the maximum or the peak flow that can occur which is causing flood. So using this we can have, and how long it will be staying, the flood can be staying, all this information we can get an idea. So it can predict peak flood hydrograph available rainfall, catchment infiltration, characteristics, and a unit hydrograph. In this case, we use extreme rainfall event for designing the storm. Okay. So, how this design storm? How do we say which is the extreme rainfall event? So, for that, we have to discuss how we will fix the design storm, right? So, what is design storm? Storm producing probable maximum precipitation. Earlier, we have discussed about probable maximum flood, PMF, but here we are talking about probable maximum precipitation, PMP, for deriving PMF or a standard project storm, SPS, for SPF calculation. So if you remember, in case of design flood, we have said that it can be either SPF or PMF. Okay, depending on the hydraulic structure, we might either consider SPF or PMF. If we are considering SPF, then that is the design flood. So, similarly, in case of design storm also, if we are using probable maximum precipitation that which is causing probable maximum flood, then it will be our design storm. Suppose if we are using standard project storm, okay, which is causing standard project flood, then our design storm will be standard project storm, SPS. Okay, so it depends on what storm we are using. That will be our design storm. Okay. Now let's look into how to estimate this kind of design storm. So first step is storm selection. We'll do using historical data. So we'll put some threshold to the based on the historical data, and we'll get the rainfall values that are greater than this threshold rainfall. Okay. And once we get this data, then we will do selection of storm duration. In case of uniform rainfall, it will be time of concentration. If it is the variable rainfall intensity, then the storm duration should be greater than time of concentration. Okay. Then what we will do is we'll calculate the depth of rainfall. So the hydrographs that are derived from the historical data represents the time distribution of the precipitation. Okay. And from that, we can calculate a PMP, probable maximum precipitation, which is the greatest depth of precipitation available in the particular place during a given duration. So we have from the historical data. After putting threshold, we have a storm event like this. Okay. And this gives us the storm duration value, and the height of it will be the intensity of the rainfall, right? And the maximum value will be the maximum probable maximum precipitation value. Okay. And then using this, what we can do is sometimes when there is no data in some catchments, we don't have any data, and we know that that ungorged catchment has similar characteristics to a gorged catchment. Then what we can do is from the available data in the gorged catchment, the storm data can be transported to this ungorged catchment as well. Okay. And then we'll calculate rainfall duration over time and area. So spatial patterns of precipitation is specified by isotype isohydal map, and average precipitation depth over an area is calculated using the point precipitation estimate. Then what we will do is depth area duration curves and intensity duration frequency curves are generated. Then what is the procedure of determining design storm in India? So first is like we will decide the duration of critical rainfall is selected. It will be is equal to basin lag if the flood peak is interest. If the flood volume is of our interest, then the longest storm in basin will be considered. So next, historical major events are taken, and depth area duration analysis is done. Using that, we will be developing envelope curves as we have discussed earlier, which representing the maximum depth duration relation for basin. Okay. Then what we will do is we'll calculate cumulative rainfall depths for convenient time intervals using this envelope curves. Then incremental rainfall for selected duration is so we will arrange these rainfall values in incremental order. So incremental order for selected duration. Which are organized according to the ordinates of relevant unit hydrograph. Okay, so if there is a maximum flood peak, suppose in this hydrograph, this is the maximum flood peak, and this is the maximum flood discharge, right? And corresponding to this time, we will keep the highest rainfall value. So if this is second highest flood value, then the second highest rainfall is placed at this time step. Okay, like this. So we will arrange the rainfall data, and then the design storm that we obtain minus hydrological abstractions will give us the rainfall excess of design storm. Okay. So next method is flood frequency analysis, which is a very important method. So in this, what we have discussed, like in the first lecture itself, we have discussed about the hydrological frequency analysis. Which is given by Chow, 1951. He said that xt is equal to x bar plus k into sigma. What is xt? Xt is the flood value for T-year return period, and X bar is the mean of the data, and K is the frequency factor, and sigma is the standard deviation of the data. So K is frequency factor is a function of return period and assumed frequency distribution. So in the first lecture, we have seen how when the data is assumed normal distribution, how it is performing. So now we will be looking into how if the data is log Pearson or like Gumbel distribution, if it is following Gumbel distribution or log Pearson type 3 distribution, then how to estimate the flood value for a given return period. So using log Pearson type 3 distribution, so it assumes the models a annual maximum stream flow or flow data series is taken, and then we apply logarithm of the data follows normal distribution. It has three parameters unlike normal distribution. Normal distribution we have parameters like mean and sigma. Here we have three parameters: location, mu, which represents the horizontal shift in the data, then scale parameter, sigma, which represents the spread or variability, in the data, and then shape parameter, gamma, represents the skewness in the data. Okay, and suppose how we will carry out the calculation is, suppose x is the random variable in hydrology. We define another variable z, which is the logarithm of x. Okay, so since we take log of the data, then it should follow the normal distribution as per log Pearson type 3 distribution. So then we know zt is equal to z bar by kz into sigma z. So kz, how do we estimate from the data? It will be z minus z bar whole square by n minus 1, where n is the length of the data and z bar is the mean of the data set. And how do we estimate the frequency factors? It will be a function of coefficient of skewness, which is estimated as Cs is equal to n into sigma of z minus z bar whole cube by n minus 1 into n minus 2 sigma z whole square. So this frequency factor is a function of return period and coefficient of skewness. From the table, like we can find the z bar value, and after computing and using this kz, sigma z and z bar, we can calculate the zt. After computing zt, if we take antilog of zt, then we'll get the xt value, which will be the flood or flow value. Then we have term called confidence limit, which will take care of the uncertainty associated with the whatever amount that we are calculating. Okay, which is used to quantify uncertainty inherent in flood frequency analysis. Because if we are assuming the data is following log Pearson type 3 distribution, but in actual the data is not following it, so there can be some error associated with it. So we are not 100% sure it will follow log Pearson, and these whatever parameters we are estimating, location, scale, and shape parameter that we are estimating might not be the correct values. So there will be some uncertainty associated with it. So for uh, to take that uncertainty into account, we are having a term called confidence limit. So we will say that the value can the flood value can come in between a upper limit and lower limit with suppose we are saying in 99% confident that the value can lie in between this range. So in 99% we are sure there is a chance that the flood value that we are estimating will lie in between this range. Okay. So if we are considering that it is following a log Pearson type distribution and we are calculating some flood value, it will also lie within this range only. Okay. So the confidence limit indicates the range within which the true value is likely to lie within a specified probability. So the confidence interval also enhances the statistical reliability of XT estimates that we are estimating. Okay, how do we calculate this confidence interval? Is that for confidence probability C, x1 by 2 is equal to xt plus or minus f of c into se. So when you take plus symbol, it will give us the upper limit, and when you take minus, it will give the lower limit of the range. Okay. And what are sc and f of c and se? F of c is the function of confidence probability c from table, and sc is the probable error which we calculate from the formula b into sigma n minus 1 by root n. Okay. Sigma is the standard deviation, n is the length of the data set, and b is the constant that we are calculating using a formula 1.1 plus 1.3 k plus 1.1 k square. K is the frequency factor here. And if suppose the data is following Gumbel's distribution, how we will estimate K is equal to yt minus y bar by Sn, where yt is the reduced value of variate, y bar is the mean of reduced variate, Sn is the standard deviation of the reduced variate. And from that, how we will calculate the xt, the design storm for a written period t, design flood x bar plus k into sigma n minus 1. And yt, how we will calculate it, since it follows Gumbel's distribution, it is equal to yt equal to minus ln of t by t minus 1, where t is the written period. Okay. So since we have looked into a lot of theory part, let's look into few questions related to this. So the first question is flooding along rivers is known as flash flood, riverine flood, coastal flood, urban flood. So if you remember, in case of riverine floods, the flooding occurs along the river. The next question is a flood that rises and falls quite rapidly with little or no advance warning is called as flash flood, B riverine flood, C coastal flood, and D urban floods. If you remember, in case of flash floods, the flood will occur very quickly. Okay, rises and falls quite rapidly with no or little advance warning. So next question is estimate the peak flow in for a 2,500 hectare catchment area in Chola Nadu region in Tamil Nadu. Okay. So in case of Tamil Nadu, we will apply rice formula which is QP equal to CR into A power 2 by 3. For Tamil Nadu, we can take quotient of Rives constant as 6.8 into area should be in kilometer. Okay, so 2500 into 10 power 4 will be meter square if you multiply with 10 power 4. So this, if you divide it by 10 power 6, then you will get values in kilometers. So it will be 25 kilometers square. Okay, 25 whole power 2 by 3. So once you calculate this using calculator, the value will be 58.1 meter cube per second. So that's the answer B. So next question is find the peak flow of the flood with 25-year return period in a 5030 hectares area of the Western Ghats. Western Ghats means which formula you have to use? It's English formula where QP equal to 124A by root of A plus 10.4. So A we need in kilometers square. So 5030 hectares is equal to 5030 into 10 power 4 by 10 power 6 kilometers square. It is 50.3 kilometers square. So QP is equal to 124 into area is 50.3 by root of 50.3 plus 10.4. So once you solve this using calculator, the answer will be 800 meter cube per second. So this is the answer. Sorry. Option D. Then the next question is from past flood data of a catchment in India, it was found that a peak flood of 165 meter cube per second has a return period of 30 years. Find the probability of flood equal to or greater than 165 meter cube per second occurring 0 times in the next 25 years. So they have said the return period is 30 years for a discharge of 165 meter cube per second. Okay. So probability of this QT greater than or equal to 165 meter cube per second is equal to 1 by T. Okay. So they are asking what is the probability that Q is greater than or equal to 165 meter cube per second where N is equal to 0. That is 0 times it should be uh, so So 0 times the event should happen. That is equal to 1 minus 1 by T whole power N. So event not occurring, the probability of event not occurring is 1 minus 1 by T. It should not occur for 25 years. So power N we are raising. How we will calculate 1 minus 1 by 30 whole power 25. So once you solve it, the answer will be 0.43. The probability of flood equal to or greater than 165 meter cube per second occurring 0 times in the next 25 years is 0.43. So the mean and standard deviation of an annual flood series or a catchment is x bar is 220 meter cube per second and sigma is 72 meter cube per second. Okay. What is the probability of a 400 meter cube per second flood occurring in a catchment within the next 36 months? So that is here xt is 36 months. Use the reduced mean, that is y bar is equal to 0.54 and reduced standard deviation Sn equal to 1.14 for Gumbel's distribution. So they have said we know xt equal to x bar plus k into sigma. Okay. So, sorry. xt is 400 meter cube per second. So 400 equal to 220 plus k into 72. So the frequency factor will be equal to 2.5. So for this to 400 meter cube per second flood event, we need to calculate the return period. Then only we can estimate the probability of it occurring in the next 36 months. Okay. So once we get k, what we will do, k equal to y bar by, sorry, yt minus y bar. Wait, let me correct it. 100. Yt minus y bar by Sn. This implies k is, we have already found it's 2.5. Yt minus y bar is 0.54 by 1.14. So by solving this, we can get yt value as 3.39. And when it follows Gumbel distribution, we know yt is equal to minus ln of t by t minus 1. So by solving this, how do we solve this? So ln means to remove ln, we have to natural logarithm, you have to apply e power, exponential power. Okay. So once you solve it, the return period we will get is 30 years. Okay. And now what they are asking, the probability of the flood occurring in the next 36 months. That probability is equal to 1 minus 1 by t whole power n. 1 minus 1 by 30 whole power 3. So once you solve this, you'll get the value as 0.0967, which is equal to 9.67 percentage. There is 9.67 percentage chance that the flood can occur within the next 36 months within the catchment. Answer is C. So the next question is an annual flood series of 40 years. So that means n equal to 40 years. For a river has a mean x bar equal to 4280 meter cube per second and standard deviation sigma equal to 1860 meter cube per second. So using Gumbel's method, the flood value for a time period of 250 years is xt equal to 12390 meter cube per second. What is the 99 percentage upper confidence limit of this variate? Take function of confidence probability as 2.58 and frequency factor as 4.36. Okay. So then what we have to do, we know that they have given the flood value for the written period of 250 years, and also they have given mean, standard deviation, frequency factor, everything. So first, what we will try to do is to calculate the confidence, upper limit of confidence. The formula is xt plus f of c into sc. Okay. So f of c they have told for 99 percentile, the f of c will be 2.58. Okay. And xt also they have given it as 12390 meter cube per second. So we have to calculate only sc. So how do we calculate sc? First we have to calculate p. P equal to root of 1 plus 1.3 k plus 1.1 k square. So they have given frequency factor of as a 4.36. Okay, root of 1.1.3 1 plus 1.3 into 4.36 plus 1.1 into 4.36 square. So the value will be, p value is 5.21 and sc is equal to, standard error is equal to b into sigma n minus 1 by root n. Okay. So it is equal to 5.21 into standard deviation is given as 1860 by root of number of data points is 40. So once you calculate this, the standard error will be 1532 meter cube per second. So the x1 by 2, the upper limit will be xt plus f of c into sc, that is equal to 12390 plus 5 plus 2.58 into 1532, that is equal to 16375 meter cube per second. So the answer is option C. So this is our upper limit of the confidence interval. So the next question is, a flood of certain magnitude has a return period of 25 years. What is the probability of exceedance? So if you remember, the probability of exceedance is 1 by t, that is equal to 1 by 25 is equal to, once you calculate, it is 0.04. If you have to convert into percentage, you multiply with 100. So that is 4 percentage. So next question is, if T represents the return period of the flood peak of magnitude Q in a catchment, what does T signify? Option A flood peak of magnitude Q occurs once in T years. Option B, a flood peak of magnitude less than or equal to Q occurs once in T years. Option C is, a flood peak of magnitude more than or equal to Q occurs in T years, once in T years. Option D is, a flood peak of magnitude Q plus or minus 0.1 Q occurs once in T years. So if you remember, the flood peak of magnitude more than or equal to Q occurs in T years is the return period of the flood peak of magnitude Q from the definition. So for a given annual flood series, which of the following represents the general equation for frequency analysis for xt? Where x is the return period, which is general variate x of return period t years, x bar is the mean of the variate, sigma is the standard deviation of the variate, and k is the frequency factor. So if you remember, we have written the formula xt equal to x bar plus k into sigma. X bar is the mean, k is the frequency factor, and sigma is the standard deviation, where xt is the flood value for a return period t years. Okay, so the answer is option A. So let's look into theory related to the risk, related to the terms like risk, reliability, and all. So what is exactly risk? Okay, the probability of occurring of an specific event X by consequences or impacts associated with that event. So we are saying that previously we have seen, like, there is a flood magnitude of 1000 meter cube per second. It can occur with a written period of 25 years, right? So if we are building a structure, hydraulic structure, for this 25-year return period, flood event, then what is the risk associated? So if because more than this magnitude, if the flood occurs, the hydraulic structure can take. So it will cause loss of life on the people that are staying in the downstreams, or the property loss, everything, right? So we need to know the risk that we are taking by building a hydraulic structure for 25 years return period. So that's what will calculate whenever we are trying to design a hydraulic structure. First, we should know what is the risk. We will try to minimize the risk associated with it, and using that we will calculate the flood magnitude, which is good enough. Suppose we need only 10% risk to be associated with this hydraulic structure, then we will get the flood magnitude value for the 10% risk. 10% risk, and we will design the hydraulic structure for that flood magnitude. So risk is probability of occurrence of a specific event X by consequences or impacts associated with that event. So basically we are calculating probability of x greater than or equal to xt. So xt is the flood magnitude of written period t, and we are designing the structure for that, and we are checking the probability of a flood that can have a magnitude greater than or equal to xt. So it occurs at least once over a period of n successive years is called risk. Okay. How risk is calculated is it's 1 minus p whole power n. That is 1 minus 1 minus 1 by t. Probability of occurrence p is 1 by t whole power n. Okay. And now we'll look into few other terms like reliability. It measures the measure of dependability and trustworthiness of a system or structure in withstanding extreme events. Is calculated by r equal to 1 minus r bar, that is 1 minus 1 by t whole power n. So there is one more term called safety factor. So from frequency analysis or any other method, we will have some design flood magnitude. But what we will do is we will try to apply some numerical factor and increase this, and we will design the structure for a little bit of higher value. Okay, so it is the numerical factor applied to design capacity of a structure to provide a margin of safety against uncertainties and unexpected conditions. Okay. Safety factor for a parameter m is given as actual value of parameter m adopted in design of project by value of parameter m obtained from hydrological considerations. This is equal to CAM by CHM. There is also one term called safety margin, which is calculated at CAM minus CHM. So till now we have discussed what are the causes of floods, how we will design, how we will estimate design flood. Okay, and now we will talk about what are the flood control methods that we can apply. So what is flood control? The action taken to lessen the harm of the floods that is caused to people or the property is called flood control. But flood control means we are reducing this loss like to 0. Okay, which is not possible. So that's why we are using term called flood management, which means like we are trying to manage the loss that is occurred due to the flood. We are not 100% reducing the loss. Okay, so different flood control methods. There are basically mainly two types in that. One is structural flood control method. In this, we have examples like dams and reservoirs. So, and next we have structures like leaves and flood embankments. Okay. And next we have structures like flood waves or channels. Next we have channel improvement. So channel improvement means like if we increase the size of the channel and reduce the roughness or increase the slope, what will happen by increasing the hydraulic radius, the discharge will increase. So once the discharge is increasing, the flood level will decrease at a point, right? So by improving the channel conditions also, we can reduce the flood event. So the next one is watershed management and land treatment. So in this, we aim at reducing or delaying the runoff before it reaches the river side. Like we are developing vegetation and soil cover, or measures like we will apply measures like increasing infiltration capacity of soil and reducing soil erosion, etc. That we will do. Mainly, it is useful for small and medium range floods. The next one is drainage improvement in urban areas. So the surface congestion and stemming from inadequate channels, which are the main cause of flooding in urban areas. So by increasing vents and enhancing outfall conditions, we can uh, uh, improve the loss due to the flooding events. And then we have non-structural flood control methods. That first one is floodplain zoning. So as you have mentioned, what is floodplain? What we will do is we have zones in the floodplain, so which are nearer to the river will be, uh, we will restrict the encroachment, like only structures like parks or something like that only can be constructed in the zone 1 area. In zone 2, less important structures like residential can be constructed, and in the third phase you can construct the hospitals, so which should not be easily affected by the floods. Okay, so like this we will have a fixed restrictions that can be applied for the floodplains. So then, using flood forecasting and warning. So if we know the how much of flood can occur and what time, we can apply mitigation measures, and we can uh, use these predictions effectively by giving warnings also, right? And doing flood proofing. So like we can apply like comprehensive strategic measures which can be non-structural also, and minor structural in case of emergency conditions. Fourth one is evacuation and relocation. So if from the flood forecast, if we know there is a flood that is going to happen, we can evacuate the people staying in that and relocate them to areas which are not affected by these flood events. Okay. The next one is flood insurance. Okay, the damage due to the flood can be covered by with these kind of insurances, right? Now let's look into few questions related to this topic. So the first question is, what is the relationship between the risk and reliability? So we have written reliability is equal to 1 minus risk. Okay, so RE plus R bar will be equal to 1. So send this to the left hand side. The option is C. The actual value of the parameter used in design of hydraulic structure is F actual, and the value of same parameter based on hydraulic consideration is F hyd. What is the safety factor of this parameter? If you remember, safety factor is given as F actual by F hydraulic condition. So the answer is option C. So the next question, a structure is to be designed for a flood magnitude of safety margin. SM is equal to 2220 meter cube per second, and a flood magnitude safety factor is equal to 1.44. So they are asking us to calculate the actual design flood. So flood margin is given as F actual minus F hydrological, and safety factor is F actual by F hydraulic. So from this, F actual is equal to 1.44 F hydraulic. And once you substitute in the first equation, Fa minus Fh equal to 2220, then 1.44 Fh minus Fh equal to, so 0.44 Fh equal to, so hydraulic design flood is, by solving this, we'll get a value of 5045.45 meter cube per second. So actual design flood is equal to 1.44 times of hydraulic. So 1.44 into 5045.45, that is 7266. So that is option D. So obvious, every time the actual flood design will be higher than the hydraulic flood design that we obtain. So next question is, a structure has a flood magnitude safety margin FSM equal to 24,000 meter cube per second, and hydraulic design magnitude is equal to 101,000 meter cube per second. They're asking us to calculate the safety factor. So F actual is equal to, sorry, safety margin equal to F actual minus F design. So F actual equal to safety margin plus F design, 24,000 plus 101,000, that is 1,25,000 meter cube per second is the F actual. So to calculate safety factor, the formula is F actual by F design. So it is 125,000 by 101,000. It's equal to, once you solve it, the value is 1.24. So option B. So next question is the hydrologic risk of a 100-year flood occurring during the 2-year service life of the project. So hydraulic risk is defined as 1 minus 1 minus 1 by t whole power n. So here written period is 100 years, and for a duration of 2 years we are considering. So 1 minus 1 minus 1 by 100 whole square. So once you calculate it, the answer will be 0.0199. So if you multiply with 100, you will get in percentages, that is 1.99 percentage. The next question is, a spillway is to be designed for a flood peak of next 18 years, n equal to 18 years, and the acceptable risk is R bar equal to 12%, that is equal to 0.12. We have to calculate the return period. So the formula is R bar equal to 1 minus 1 by t whole power n, that is 0.12 equal to 1 minus 1 by t whole power 18. So 0.88 equal to 1 minus 1 by t whole power 18. So once you solve that, the return period will come as 141 years. So nearly we can take that as 140, approximately 140 years. If you calculate that, this equation, okay. If you have any doubts, you can stop in the middle. Stop me in the middle. So the next question is, among the following methods of the flood control, identify a non-structural measure of flood control. So option A is floodplain zoning, option B detention reservoirs, option C channel improvements, option D leaves. So we have seen that floodplain zoning comes under non-structural flooding measure, and all these three are structural measure of flood control. So the answer is option A. Next question is, kind banks are provided in rivers to option E, increase the depth of flow in the river, B, decrease the velocity of flow in the river, C, channelize the flow of the river, and D, reduce the floodability. So guide banks is little bit like embankments only. So as I have told, so what they do, we will raise this height. Okay. So we are trying to channelize the flow in the river. It doesn't affect the depth or velocity and flood peak. So mainly we are trying to channelize the flow of the river in this case. So the next question is, which of the following methods help to reduce flood damage by channel improvement? So we have discussed that reducing the sorry reducing the channel roughness, okay, reducing the channel roughness, increasing the hydraulic radius, and increasing the slope will reduce the flood damage in case of channel improvement. So the answer will be removing vegetation of a channel parameter, because once you remove this vegetation, the roughness will reduce. So it will increase it can take the discharge will increase. So which causes reduce flood damage. The next question is, which of the following is not a feature of floodplain zoning? Option A, controlling population. Option B, preventing encroachment. Option C, regulating land use. Option D, dividing of areas into zones. As you have told, if there is a river like this, we have multiple zones on other sides, zone 1, zone 2, zone 3. This is the major area that can get flooded easily. So we will try to put land use restrictions on this area and prevent encroachments. Also, we are dividing the floodplain areas into three categories mostly. So here we will allow areas like playgrounds or parks, etc., which even though they get flooded, there won't be any damage, much damage. And it is in second zone, residential area, government offices, all this we are allowing, which will get very less frequently flooded. And in third case, we are putting buildings like hospitals, which are very important. You should not let these kind of buildings get flooded, right? So we are also putting regulation on land use and preventing encroachment, and also dividing the areas into zones. So all these three we are doing in floodplain zoning. One thing more we are not doing is population control. So the next question is, which of the following combination of for a channel is more suitable to achieve the best result in flood management? Option A, increasing width and roughness. Option B, increasing width and reducing roughness. Option C, decreasing width and increasing roughness. Option D, decreasing width and roughness. So if you remember, if we reduce the roughness, the flow magnitude will increase, so it will cause less flooding will reduce. And if we increase the width of the channel, it can accommodate more volume of water, right? So the overflow of water cannot happen that easily. So then also flood events can reduce. So the best result will be increasing the width and reducing the roughness of the channel. Next one is, what is the ideology behind using watershed management method to manage floods? Option A, completely to prevent the occurrence of flood. Option B, reduce and delay the flood. Option C, use all flood water for practical purpose. Option D, send all the flood water to underground storage. So it's option B, always reduce and delay the flood event. So in today's lecture, we have talked about floods. So, what are types of flood? What causes floods? How flood affects the area, people, or the property that is in the area, and what is the severity of the flood? and also how to design a hydraulic structure for a design flood. We have discussed different methods of designing this flood magnitude. Also, we have discussed about the risk terms like risk, reliability, safety factor, safety margin when you're constructing a hydraulic structure, and also different types of flood management methods that we can apply, which are like structural or also non-structural. So, if you have any questions related to this uh, topic, I can answer you. Otherwise, we can end this session. So, if there are no questions, let's end this session. Thank you for listening.